What's up, everybody? This is going to be episode number 41 of Rolling with Reason. I have done a lot this week and I've learned some valuable lessons, I think. This week in particular, I think one of the biggest lessons that I've learned is even though maybe we're not using a lot of different media platforms and entertaining ourselves in that way, it's still very easy to misuse search engine related tools and or misuse the textbooks that you have. So as you guys can tell in these videos, I have a lot of different textbooks and things that I like to use for learning my coding endeavors. And that's primarily because it's hard sometimes to tell the difference between what is foolproof and what is not when using AI tools to learn. That's not necessarily um, it's not a bad thing at all, actually. I think it's a great thing because then you're helping the authors and the people that write these books, and then using that information to be able to move yourself forward within that specific environment. And I think that's crucially important. I think for any time that we're learning, and maybe a good utilization is understanding what you're reading, and then if you come up on a problem that you can't understand, maybe instead of going to a forum for hours or looking to other people for answers, we can actually just maybe use AI and then use contextual clues to be able to represent what it is that we're trying to figure out, and then we can move forward. I think if you do it that way, there's actually like a very good chance that you understand what you're doing, and it's no problem. However, though, if you're like very vague with your questions, I do think AI can still produce false answers in a way that maybe um, there are slight details, but slight details can add up to an overall picture problem. And so I think that's something worth bringing up, just kind of how you're using these tools. If any of you guys out there are using these tools and doing that thing where you're reading stuff and you're learning, and then you're trying to also learn from these AI tools. They may give you the answers, just I guess make sure that you're becoming knowledgeable within what you're asking. If not, maybe maybe pick up a actual book instead, or read the actual forum or whatever that be. Yeah, so this week, I guess I'm touching on this too because I've done a lot of context switching. And so what I mean by that is I think I've been dipping my toes into a lot of different sections, and I think that's great to a degree. Like I think if naturally we have the inclination to switch context rapidly, I think that's a good thing, especially if it's within a domain like this one. But I think you can still do it too fast. And I think sometimes, a couple of times actually, I've read multiple books now. Um, Whenever you get done with a book, instead of like trying to find the next one to traverse to, maybe actually just take the time to build the stuff out of the book that you just read. And I think that's true because that builds in that kind of like retention for a long span of period of time where you're working on retention recall, and that actually hardens your memory in association with the subject that you just learned. You can, though, switch between books too rapidly. So in my case, as I said, I was maybe taking, or I am taking a course, and so I'm going through that material, and then I'm also kind of pairing books with the course as well. So I can kind of double up on what I'm reading and understand what I'm reading. That plus, I think some of the material looks as though it may have been generated for sure. And so, really taking the time, I guess, for me, myself, to understand what I'm actually going through is more important than just kind of like super, you know, doing like super passes and not really understanding it. Like, if you're reading for retention versus reading for generalities, that's one thing. I think you guys remember me talking about getting burnt out, reading Dead Simple Python, and then being like, man, like that was a lot, and it kind of killed me a little bit. But this time around, I'm reading in conjunction with what I should be reading. And so that generalization does help tremendously, but I can tell you now, looking back when I'm like, oh, like I really do need to spend more time on that particular subject. And so that being said, I think that same thing can be said for a lot of stuff. But if you're reading in generalities and you're learning something new, and it's like your brain is just like a sponge when it comes to something new, I think it's more important that you take the time to really comprehend what it is that you're reading, and maybe not do such a general pass. But if you're reading in generality, and then you're also reading curriculum to perform maybe some type of project or something in conjunction with, that's going to be a big determining factor between the difference of what is or what isn't beneficial in that scenario. So I guess there's some variability there for sure, but I noticed that I was switching between a lot of books very rapidly. And then what I realized is that my retention for some subjects are kind of going down unless I take the time to rehone those skills. Now, I guess to some degree, I started building a Django project this weekend, so that was very cool. It's for a company. And so when I was building that project out, I was having some problems. And then so here's another issue too with using AI. We can use AI to build up the boilerplate code, but if we're not remembering by reiteration how to build that code from scratch, and then we have it start generating on top of that, I think that's when we quickly run into that problem of where we can run into a code base where we don't necessarily know what's going on. And I think that's a very easy thing to do if you don't take the time to understand what's being generated for you and then thoroughly going through it. In my case, I feel though as if I should be able to definitely move some of the boilerplate code forward, but then I quickly realized once I got to a point, too much was generated, and then I thought there were too many abstraction layers. And so removing a lot of those abstraction layers will be what makes it easier, I think, in the general um, long run for that particular website. But I would say I'm probably about 85% of the way done with that website. But now I have to remove a bunch of clutter that otherwise I normally probably just wouldn't have put in the first place. And so I think that's an interesting hindsight thing. I think AI can do great things and I think it can generate wonderful code, but if you don't take the time to understand what it's generating, when it's generating it, and then actually comprehending it, you're gonna, if that's a foot gun, you're gonna trap yourself. And so doing a quick, I guess, doing deep methodical questions in association with AI when you absolutely have to is going to be the best route, I think, for learning with AI. And then as far as the textbooks are concerned, I think those should be your foundational primer before you have to ask questions to the AI. So if you're really curious about a subject or something, you should really dive in with a book and then maybe come back and, or if you're stuck, right, use AI to try and work your way through what you're stuck with. But switching very quickly between textbooks, I think, is a harder thing. And I think being mindful of how you're doing that is going to be important. And then there's this thing too where I can learn something for a while and then I kind of deviate away and then I have to come back and I'm like, "Oh man, what's going on here? This is hard." I mean, it's supposed to be hard, like don't get me wrong, and I think that's going to be what builds up the overall retention over a longer span of time, but that is difficult, and so I think maybe like dropping like seeds of little study sessions with previous topics will be what maybe moves us farther forward. But now I would love to just kind of do like a rant, and I think I'm going to do a rant, and we'll probably end up closing this episode up after this because it's going to be a lot. You guys are going to feel me. So, the book I started reading, How AI Works. Okay, this book um, is by Ronald T. Knuzel, I think is how you say his name. I've actually kind of read this book before. I would say like excuse me, the first couple chapters, and I noticed that once I got to a certain point, I thought, well, I definitely need to do some other reading to be able to be up to par with what this book is talking about. But the first chapter is kind of a generalization of what AI is and kind of giving us an idea into what the difference is between what people talk about in the media today and between where we're at. Now, granted, he was writing this book, I think, somewhere around 2022. So it's, three and a half, you know, 3.25 years old now. And I think it's worth saying that that could be outdated in terms of AI standards to some degree, but I don't think, uh, it depends on the context that you're talking about. No pun intended for any of my AI or development people out there. But yeah, I think he goes through and he just kind of breaks down the misconception of what AI is. It's kind of like a AI demystified type of book. And then we get into the second chapter and he's talking about the history. And so the history actually predates like pretty far back. I think in the 1960s almost when the AI came about before what it is today. And so that AI was that AI was artificial intelligence, but it was algorithmically implemented by a set of rules to a degree. It was very general, and so I guess to kind of give the definition to what algorithm is, that is a set of steps or sequences performed in a specific pattern, and that can be done programmatically. And so we can have things as simple as what we call decision trees, which is just like yes, no's, right? So it's like, do I want ice cream? Yes. Is it healthy for me? No. Like, or I don't know, something along the lines of that, right? And so that was like very general old school AI, and it could go definitely a bit deeper than that. But then we could also talk about how it was brought up, but it was never used as much as it was, but the computing power was actually lagging in comparison. And then I believe in like the 1980s, it was brought up again. And here's a staggering, actually, estimation of the compute difference. From like the 1980s until like 2022, I think the compute power difference was almost 110 billion times better and faster today than it was in 1980, just to give you guys an idea. The crazy thing is that we all think that AI is new and it's booming and it just like happened all of a sudden, but that's really not the case. So, in the third chapter, we start getting into these classical machine learning models. So, I guess I should go ahead and touch on that. It's kind of like there's two subset categories. So, there's AI, machine learning, and then deep learning. Deep learning is a subcategory of machine learning, and then machine learning is a category of AI. So, like I said, AI, like traditionally, is just like an algorithmic style type of thing. There's no learning there. It's just like a rule set. It's kind of like literally a list of actions that it takes. It's very basic. And the machine learning is a little different because then it starts to use what's called models, and then those models are trained, and then it gives better deterministic outputs based off of probability, I guess is maybe a way to phrase it. And then we have deep learning, which is using neural networks in conjunction with models and a whole slew of other stuff that I won't go too deep into. But chapter three breaks down three classical models. And so the first one's going to be nearest neighbor, the second one's going to be random forest, and then the third one will be a SVM, which is a support vector machine. Now, the nearest neighbor is actually the simplest one. There's essentially no training phase to what is the classical machine learning, the classical ML model. Um, Nearest neighbor. And that's because we have data. And so I guess to think about data and talk about data for a second, we pretty much have a container or a list, and it has X amount of items in it. Those items within that list are what makes it kind of unique. We call those features, and we actually call the list a vector instead of a list or a container, even though conceptually in terms of programming that's what it would look like. And so we have these and we call those feature vectors, and then we'd have a lot of feature vectors, so we would have a lot of lists talking about the same thing but maybe with different numerical inputs in them. And so what happens is once you get a stack of those vectors, we call that a matrix, and we use that matrix to pass into the model. And so, and this first classical ML model that we're talking about is the nearest neighbor. It uses it uses distance to try and calculate how to identify something. I think maybe an easier way to just talk about this for a moment is kind of thinking about maybe like a scatter plot. So if you guys remember, we have like the square grid, and then we have like X, and then we have Y. And so we have 0 and to infinity, 0 to an infinity. And let's say we have something that is very similar, but we have 50 of them. If we plot those and we put those onto that grid, they're kind of going to be in the same general area here. And then let's say we have blue, and then we plot them and there's 50 of them. We put them on the grids over here. So there's like a distinct difference. There's like two different groups here that reside. And so if we added in, like, let's say we wanted to guess, we have a new circle or whatever, but we don't know if it's red and we don't know if it's blue. Well, if I throw it at that scatter plot and it lands in the red area, it's probably a fair assumption to say that it's probably going to be red. But if I throw it on there and then it's over by blue, then it's probably going to be blue. So that's one of the biggest pros, I guess, of the nearest neighbor plot. I guess if you think about it simply like that. And I think it's a good introduction to kind of what is machine learning and what is kind of this subset of AI with these models. It does that, and when we throw on that new unknown sample, that's actually what we would call that, an unknown sample. When we throw that unknown sample on there, it could be k to the nearest 1, 3, or 7. And so what that means is it will stretch out and measure the distance between the closest 3 points to be able to classify something. And so we have classes, and that's how we actually say what the unknown sample is. And so in this particular case, that's what a nearest neighbor model does to a degree, but the data set is the most crucial part. And so there's no training. You actually just give it the data set and then it looks at the data set. And when you give it something unknown, it makes a prediction based off of what is the data set. And it does that by distance. Now, it should be noted though that the nearest neighbor model is extremely slow, and that's because it has to calculate the distances. It also has a problem that is known as the curse of dimensionality. And so, to talk about that for a moment, if you were to think about a computer screen or your smartphones or anything like that, they're actually composed of little teeny bite like pixels. They're super small. They're very hard to see. Like you could see them more on the older TVs, not so much now on the newer ones because they have so many pixels. But maybe if you got a magnifying glass. But so if you think about it in that way for a moment, we have images and they're just composed of pixels. And so the first type of data set, or maybe one of the predominant ones, was the one called the MNIST data set, which was some numerical data set comprised only of a certain set of numbers. And so that was used, and that was in a 28 by 28 grid pattern. So that actually means, if I'm thinking about it correctly, it's 700 something plus dimensions. And like, what does that mean? Well, it means that every single pixel is actually a dimension. And so what's happening inside of that nearest neighbor model when we give it that data is one of those feature vectors is going to have 700 and something values in it. Now, let's say you have 700 something dimensions though, right? So that's kind of going to be the variability of how that can be, um, how the correlation can be drawn. And so if we have 784 dimensions, we're actually going to want about 700 samples. So 700 vectors. We're going to want that many plausible representations, and that will help with that. But having even more is actually better. But I do believe there's a threshold there as far as accuracy is concerned in association with that. And it's just quite an interesting model. It maybe could be used earlier on in a process um, to make sure you're heading down the right road, but then maybe you would swap it out later for something else. And that's kind of going to bring us into what is the random forest. So, the random forest actually has a three-part stage. The random forest does this thing called bagging, which uses with replacement type of randomness. And then we have the next portion, which is going to be the random feature selection. And then the third part of that is going to be what we call ensembling. And so to talk about bagging for a second, actually, let's just talk about like a forest in a second, right? A forest is just comprised of a bunch of trees, right? And so the process here essentially is we give and pass in some data, remember, so our stack of vectors, and then we want to essentially manipulate that data so it has duplicates, but it doesn't give it more features. So I guess a good way to think about it is if you had the numbers 1, 2, 3, 4, and 5, and that was all that was in your little list, your little vector, your little container. If that's all that you had, um, you would want it to randomly populate possibly a duplicate. So it could actually go 1, 2, 3, 4, 5, and that's it. Or it could go 1, 1, 3, 4, 5. And so that adds a randomness because it actually takes place on um, every single vector that's inside of your data set. And so what you can do is you can actually use that, or you don't actually use, I mean, you use it, but it's just there. It's a part of this random forest model process. And so it goes through and it swaps out all of that data, but it doesn't produce any new data in essence. It only does duplicates. And so it will make a replacement or it won't, essentially. And so that's that first process. And then the second process is where we have the decision trees themselves that are made. Um, but that is done through what is called feature selection. And so the feature selection will be what selects um, a random set of particular values out of the list. So in our example where we have 1, 2, 3, 4, and 5, it could pick, oh, okay, we're going to go with the 1 column. And so that means for every single stacked vector, it's going to take out all of the 1s or all of the 3s or all the 5s. And that's going to make one of our trees. And then we have ensembling. And ensembling is essentially a composition of all of those individual tree branches or trees that create the forest. And so if you remember at the beginning, I was talking about decision trees in general, where you kind of have this pattern where it weaves through and then it makes a pick. That is essentially what is happening here, but with numerical values for placement. The ensembling portion is what brings all of those together to predict a class identifier, essentially. It's what lets it work together to figure out what's going on. Now, that is a pretty robust, actually, classifying system. But one of the biggest problems with it is the amount of time it takes to actually give you a classified label. And that's just because it has to go through all of those trees to try and decide what the actual answer was. Random forest are, I would say, actually probably one of the better options, but again, they kind of have this slower problem. And not to mention how much bigger your trees grow based on the amount of features that you have again. So meaning that you're going to need more training data because the random selection of the features is going to be a big determining factor of what some of your outcomes are. But there is also something to be said that you could train multiple random forest models. You could take their outputs and then compare them against each other. And generally, the strengths of that are going to outweigh and actually be pretty beneficial. But the other thing to note here in that particular scenario is that it's only going to give you a um, answer, but it's going to take a long time before it gives you that answer. Essentially, is what I'm trying to say. And then, so that kind of wraps up what the random forest is. It's just a bunch of decision trees. We give a data set. It can make some duplicates based out of the single sets. And then it actually goes into that process of where it uses random feature selection to make the actual little trees, the little branches. And then it goes through the trees and the branches to classify whatever that unknown sample is that we throw at the chart, essentially. Now to talk about the SVM, this is actually one of the more complex ones. It actually has a four-part mechanism in it, actually has a little bit more math. And he even acknowledges in the book to not go through the math because it's kind of crazy, even for some math people. And so I guess just there's a good way to think about support vector machines. It's got four parts. First part's going to be the margin. The second part is going to be the optimization, actually support vector, optimization, and then the kernel. And so, in a nutshell, we have those two areas of points again. That's going to be our data sets, right? And so we're going to pass those data sets and we want to plot them. And the way that that's going to happen is based off of their values, of course, so dimensions, features, etc. But it needs to happen in a way that is practical for us to understand, I guess, on this podcast. And so to think about it, there's that separation. And so what we do is we essentially say that there's a separation like right here between. And that is actually going to be our margin. And the way that we find our margin is with the optimization and the kernel. The support vectors are the distinguishable points that those lines will actually fall on top of. So what does this mean and what am I saying? Those points exist and we're going to plot these lines based off of that optimization and the kernel. As I said, the optimization is picking the best possible points. So the best possible vector with the most outlandish feature or dimension, I suppose you could think about it in that way. And so that's going to be where you place one of your lines. If there's 2 points that are actually like in a straight line with each other, and then you have like an outlier, it's going to map the 2 point line probably before it finds the outlier. But those points, those 3 specific points or 2 points for the dashed lines for your margin, those are your actual support vectors. Now, the optimization is what's used to find those particular points. And then to talk about the kernel, there's a lot of different kernels that could be used. Not a lot. I hesitate to say a lot because I actually just don't know. But the one that you run across the most common is the linear kernel. Linear function kernel. You also have a Gaussian, and then there is a, I believe, bias function kernel, something along those lines. So those are just other ways to figure out how to work with more complex data. But for now, I think it's easier just to know that the linear is the most common one that's going to be used, and that's kind of what finds your boundary line. So the boundary line is going to be exactly what splits those two margin lines. And so that's pretty much going to create these two fields. And then right between my thumbs right here is going to be that boundary line. And so anything that gets plotted within my outside fingers is going to be classified in that way. And so that's kind of that process, I suppose. And that's pretty much it. The biggest first step is just kind of getting through that training phase and marking out where that marginal area is. And then once you feed it in data, it does pretty well at classifying. Um, you would think, but some of the other models outperform an SVM. But when you trade out the SVM traditional linear style kernel and you use something like the biased function, that actually has a better outcome, but it takes a little bit longer if I'm not mistaken. It's also not the best either in terms of accuracy. And I guess maybe that's one final thought to bring up before I close this out is the accuracy. The accuracy is something that is done with the test samples. And so when you go to train a model in the first place, you feed it in all of this data. And then you can make the classifications out of that data. Um, you retain a certain percentage of what was classified in the training phase, and you use that to try and see if the model is working correctly. Because you refeed it in that data, then you'll know how well it's going to perform, and then you can throw unknown variables and stuff at it. But I will say I'm a little fuzzy on that part right now. But I think this is probably a good stopping point. I think you guys can understand how maybe me talking about this and then thinking about me building web development projects or web apps, and then also learning this on top of that, it's kind of like two distinctually different things. And I think I can definitely overload my head and my brain with this process. And so, really just taking the time, making sure you've honed in and focused up on and really just done a good job at learning the first thing first before you jump into too many different things at the same time. It's probably going to be more beneficial in the long run. But yeah, this was Rolling with Reason, episode number 41. I hope you guys like this a lot. I think we're going to have a philosophy episode next week. I'm going to pick up a book and read that. What book? I'm not sure yet. I thought about reading another variation of Meditations by Marcus Aurelius, but I also have Letters of a Stoic and some other things that I could pick up as well. I kind of like Stoicism, so I guess I should read that. I still also haven't finished the Gulag Archipelago that's sitting back there, so maybe I'll finish that up and give some more conceptual thoughts on that. But this was episode 41 of Rolling with Reason. So thank you guys for listening. It's been a long week, but it's going to be a better week coming up. You guys have a good week. Thanks, everybody. Peace.
Thanks for listening. Stay resilient, embrace the struggle, and keep moving forward.